Hi, welcome back. Okay, let's continue on to discuss about two-way ANOVA analysis. Okay, we're going to take a look at this example 4.2. Okay, let's start. A chemical engineer studies the effects of various reagents and catalysts on the yield of a chemical process. The yield is expressed as a percentage of a theoretical maximum. 2 runs of the process are made for each combination of 3 reagents and 4 catalysts. The data is given as follows. Okay, first class, let us try to identify, let us try to understand what are the 2 independent variables and what is the dependent variable. Okay, now factors and response. Okay, 2 factors and 1 response. Now, from this statement up here, we can see that they are trying to see the effects of reagents and catalysts on the yield of chemical process. So we can easily understand that reagents and catalysts are the 2 factors here. Okay, so what is the response? What's the dependent variable on the yield of a chemical process? So yield of a chemical process, okay, this is the dependent variable. So the 2 factors are reagents and catalysts, and the response is yield of a chemical process. And then down here we can see that it has explained to us that there are 3 reagents and there are 4 catalysts. So reagent has 3 levels and catalysts has 4 levels. So how should the chemical engineer conduct this experiment? Okay, first, the chemical engineer has to conduct this experiment in a way that he or she needs to consider all possible combinations of treatments. Okay, all possible combinations of treatments from both factors. So you see here in this table here, first, the chemical engineer conduct first experiment by considering catalyst A, region 1. Next, this one is catalyst B, region 1. Okay, the next treatment, catalyst C, region 1, and so on. Okay, and we can also see that in this table, one cell here represent one treatment. And if you count the total number of cells inside here, there are 12 cells, meaning that there are 12 treatments in this experiment. Ataupun you can also use the formula. Okay, I have already shared with you the formula to calculate K. K is equals to A multiplied by B. So here, A is this catalyst here. Okay, so A equals to 4. And region here is B. B equals to 3. Okay, so how many treatments? K is equals to A multiplied by B. So 4 multiplied 3 is 12. So this is another way to calculate lah how many treatments. And we can see that in each treatment, in each cells, okay, the table gives us 2 data. Okay, here, this is first data, this is the second data. So each cells has 2 data, which means that each treatments in this experiment has 2 replication. 2 replication. 1, 2, 1, 2, 1, 2. Okay, get it, class? So this experiment consists of 12 treatments in which each treatment has 2 replications. Boleh? Okay, so now, let's conduct two-way ANOVA analysis for this question. So, we're going to focus on question E and F. First, construct an ANOVA table. So, class, for two-way ANOVA analysis, the ANOVA table is more elaborated than the one-way ANOVA analysis. Okay, so this is how it looks like. Okay, you might feel intimidated because there's so many rows and then the formula seems so complicated. But actually, don't worry, we're not going to test you on all of these formulas. Okay, we have decided, all the lecturers have decided that for this semester, we will skip these 4 formulas. 1, 2, 3, 4. Meaning that you don't need to use these 4 formulas for this semester. So if we were to assess you on two-way ANOVA, okay, we will give you the value of SSA, SSB, SSAB, or SSD. We will not make you use these 4 formulas, okay? 1, 2, 3, 4. But the other formulas are very easy. So yeah, you need to learn up on how to use all the other formulas to calculate SSE, okay, to calculate degree of freedom for all the rows, and to calculate the mean of squares, to calculate f-test, and to calculate critical value. So first, in the two-way ANOVA table, you have the first row is for the row effect. Okay, for this case, the row effect here is the catalyst. Okay, and then the second row is for the column effect. The third row is the interaction effect. Fourth row is for error, and the fifth row is for total. Okay, so that's how the two-way ANOVA table looks like. Okay, row, column, interaction, error, total. Now, kita tengok soalan tadi lah. Okay, let's look at the example. So, for this semester, as mentioned just now, I won't make you use the formula for SSA, SSB, SSAB, and SST. So most probably we will provide you with these 4 values. Okay, so let's take a look at the other formula, SSE. SSE is equivalent to SST, okay, this one, minus these 3 values. Okay, so 1440.04, you minus this, you minus this, and you minus this, you will get 354.2900. So that is the SSE. Okay, what about degree freedom for factor A? Degree freedom for factor A is equivalent to A minus 1. So can you recall how many levels does factor A has for this example? Our factor A here is the catalyst. So there are 4 catalysts, kan? So 4 minus 1 equals to 3. The second degree of freedom, which is for factor B, is B minus 1. Okay, so there are 3 regions. So 3 minus 1 equals to 2. Very simple. Kan? Simple je kan? So then the third one is A minus 1 multiply B minus 1. So basically, 3 times 2 you get 6. Okay? 3 times 2 you get 6. Okay. And then the fourth degree of freedom is A multiply B multiply R minus 1. Okay. Try to recall. What is R just now? R is equals to 2 because there are 2 data collected for each treatment. R equals to 2. So, A is 4 multiply by 3 multiply by 2 minus 1. So, 4 times 3 times 1. So, that will give you 12. Okay. And the last degree of freedom is capital N minus 1. So, capital N, or you can also calculate using ABR minus 1. But it's actually capital N minus 1. So, capital N is the total number of application for all the treatments. So 12 treatments multiply 2 replications, okay, minus 1. So that will give you 23. Okay, very simple formula. So yeah, you should be able to use this formula, degree of freedom. And then mean of square is calculated using the same pattern that you see in one-way ANOVA. Okay, to get MS, you just take the SS divided by the degree freedom and you'll get MS. Very simple, okay? To get MSB, you take SSB divided by DFB, degree freedom B, you get lah MSB. To get MSAB, you take the SSAB divided by the degree freedom, then you'll get MSAB. And same goes to MSE. Okay, so the pattern is exactly the same pattern as in one-way ANOVA analysis. And even for the F-test formula, it also has the same pattern as in one-way ANOVA analysis, in which to get the F-test for factor A, you take MSA, okay, MSA divided by MSE. Okay, for F-test B, it is MSB divided by MSE. So for the third F-test, okay, F-test AB, you take the MSAB here divided by MSE. Okay, so that's the pattern. To get F-test, MS divided by MSE. Okay, MS for that row divided by MSE. MS for that row divided by MSE. Okay, so that's the formula for F-test. You can just try to memorize the pattern. And for critical value, it is F alpha. All 3 critical values are F alpha. So the 2 reference number here, nu1, nu2 here, follow the degree freedom of that row. So degree freedom A is 3. Okay. And then the second nu2 is degree freedom E. So you see for all three critical value, the nu2 here is same. All 12, 12, 12 because it is the degree freedom of error. Okay, so for the second critical value is F alpha 2, 12. The third critical value F alpha 6, 12. Okay, so just try to remember the pattern. Okay, it's very easy. By practice, you'll get used to this. You'll be very good in constructing the two-way ANOVA table. So this is how you construct the two-way ANOVA table, in which you will get 3 F tests. Okay, you will get 3 F tests. Okay, yep. Hi, itu dia. Okay, now question F. Test if there is an interaction effect between the reagents and catalysts on the yield of a chemical process at 5% significance level. So you need to test, is there any interaction effect between factor A, factor B and factor A? So in this question, catalyst is your factor A. Okay, on the response using 5% level of significance. So let's recall the procedure for two-way ANOVA analysis. Okay, you kena follow yang ni. You need to start here. Start with the first stage, which is the interaction effect between factor A and B. Okay, so let's take a look. How does our first hypothesis testing in the first stage here looks like? So in your H now, okay, the interaction effect hypothesis testing, H now you're saying that there is no interaction effect between A and B, factor A and factor B. H1 you're saying that there is an interaction effect between factor A and factor B. Okay, step 2, you need to go and get the correct critical value from the table. From which table? You already established this critical value in your two-way ANOVA table just now. So jom kita tengok two-way ANOVA table. Okay, see critical value. There are 3. So which one to choose from? You choose the third row. Okay, class. The third row in this two-way ANOVA table is for interaction effect. Okay, this is for interaction effect. So you will use F test AB and F critical value here for your interaction effect hypothesis testing. Okay, sebab tu you tengok here is 2.9961. So the solution here is also choose this critical value. Okay, the AB critical value. Alright. So in step 3, you need to compare the F test AB, also from the third row. You have to compare F test dengan the F critical value. Remember class, it's a right tail test. Okay, ANOVA is always a right tail test. So let's recall how does a right tail test looks like. A right tail test means that you have the rejection region on the mana? Right hand side. Yes. So here is 2.9961. This is 2.9961. So where is your F test? 0.7. 0.7 is somewhere here. Since it falls in the acceptance region, so that's why we don't reject H null. Okay? Boleh kan? Okay. Don't reject H null. So if you don't reject H null, means that H null is true. Meaning that at alpha 0.05, there is no interaction effect between catalyst and reagents. So this is the conclusion for the first stage. The conclusion say that there is no interaction effect. So what happened if there is no interaction effect? You see here? If the result of the first stage is saying that no interaction effect between factor A and factor B, you need to go to the marginal effect, the second stage. Yep. So now we need to proceed to the second stage. Okay, so how to proceed to the second stage? First, you start with the row effect. Okay, since there is no interaction effect, test row effect and column effect. So first, the row effect hypothesis testing, there is no effect of catalysts. There is an effect of catalyst. So this is factor A. And then step 2, we need to establish the critical value here. Okay, so let's take a look at the table again. Mana table tadi? Excuse me. Okay, so since we are testing for catalyst, which is factor A, so the row effect hypothesis testing is the first row. In your table, two-way ANOVA table here, you will choose this F test A and this F critical value, 3.4903 and 7.7167. Okay, so let's take a look at it again. So here, you see, this is the critical value. And if you compare right tail test, still a right tail test. So imagine, right tail test, rejection region on the right hand side. So F test is bigger than the F critical value. So this F test falls in the rejection region. That's why we reject H null. Reject H null meaning that at alpha 0.05, there is an effect of catalysts on the yield of chemical process. Boleh kan? Okay. So done for the row effect hypothesis testing. Then you also need to do another hypothesis testing for the column effect, which is factor B. There is no effect of regions. There is an effect of regions. So this is H null H1. Okay, don't change. H null is no effect. H1 is exists effect. Okay. And then, so this one, this critical value is from the second row of your two-way ANOVA table. Second row. Second row is for factor B. Okay, so you will use this F test and this F critical value. 3.8853 and also 4.4621. Okay, boleh? So here it is. You compare the critical value and this F test and the critical value. Still a right tail test, Still a right tail test. Come on, class. You can do this, right? You understand how a right tail test looks like this. Okay, so this is the critical value, 3.8853. And then your F test is 4.4621. F test is somewhere here. F test is bigger than 3. So of course, it will be on the right hand side of 3. So it falls in the rejection regions, reject H null. At alpha 0.05, there is an effect of regions on the yield of chemical process. Done with the two-way ANOVA analysis. So that's how you conduct two-way ANOVA analysis. You must follow this procedure. You start with the first stage, which is the interaction effect. If the conclusion says there is no interaction effect, you must proceed to the marginal effect, in which you must conduct two more hypothesis testing. One for row effect, one for column effect. Isn't that interesting, class? So yeah, that's how you do it. Okay. In my next video, I will show you how to use Microsoft Excel. How to use Microsoft Excel to generate this two-way ANOVA table. So that's why you don't really need to do this manually, but you still need to know how to use this formula. Okay, you need to know how to use 1, 2, 3, 4, 5, 6, all the other formula except this 4. Okay lah, that's it for this video. Okay, I'll continue in my next video, or maybe in our virtual class. I'll explain to you about the Microsoft Excel output for two-way ANOVA analysis. Thank you for listening in. Make sure you understand this example. Make sure you understand the procedure. Yeah, I think that's all for today. Thank you, class. Bye.